Welcome, curious minds, to another deep dive. Today, we're plunging into a topic that's really cutting edge and honestly essential. Artificial intelligence in cybersecurity. You sent us an incredible stack of sources. We've got this detailed handbook covering AI use cases and also a really vibrant Reddit discussion full of learners just like you sharing their experiences, how to break into the field, how to advance. So, our mission today, we want to unpack how AI is really changing cybersecurity, what it's doing right now, and then crucially, map out a clear path for you. How can you self-learn, get practical experience, whether you're just starting or, want to go deeper?
Yeah, what's really interesting is how these sources work together. We're not just looking at the, let's say, the high-level theory of AI applications. We're also seeing the really practical, hands-on steps people are taking to understand this stuff
Right.
and even implement it. So we'll connect the dots, right, between the advanced AI concepts and how you can actually learn it. Okay, let's get into it.
Right. Let's start big picture. This idea that AI is creating a new era in cybersecurity. The handbook jumps right in talking about a unified deep learning pipeline, which sounds fancy, but it's basically a systematic way to use deep learning, reinforcement learning, to tackle different security challenges. It mentions standardizing ML pipelines, how that helps the industry.
And that brings up a key point.
Yeah.
Why is AI becoming so critical now? I mean, think about the old ways, signature-based detection, rule-based systems for finding intrusions. They struggle, especially with threats designed to evolve, to look like normal traffic. AI brings this incredible power for pattern recognition, spotting anomalies where humans just, well, they'd be overwhelmed. It's almost impossible manually.
Okay, this is where it gets really fascinating. Let's dive into some specific examples, the handbook details. First one. AI doing reverse engineering, or ARI. Traditionally, that's just a massive manual slog, right?
Yeah.
Guessing function boundaries, tracing control flows, figuring out data semantics, but AI is stepping in.
Exactly. RE is all about digging into compiled code, binaries, to understand how software works. Crucial for analyzing commercial stuff, but especially malware. The source mentions tools humans use, like IDA Pro, GDB. AI helps automate things like function boundary identification, predicting where a function actually starts and ends in that binary soup, and also function signature generation. So figuring out what inputs a function needs, what output it gives back.
That sounds incredibly tough. Compilers make things messy, don't they? Creating binary patterns that are hard to predict. How does AI even manage?
Well, the handbook lays out a few approaches. Instead of just raw bytes, which can hide the meaning, AI can look at features from the assembly code itself, the operations, the operands, or it can learn these abstract vector representations. Think of models like ASM2Vec. It's like creating a unique fingerprint for the code, which makes the AI better at seeing through obfuscation tricks malware uses.
Ah, okay, so it's more resilient to those tricks.
Precisely. These models, like Palm Tree or Instruction2Vec, are getting really accurate. Palm Tree hit high marks for function signature generation, and using one-hot encoding for boundary identification was also very precise.
So it's automating a lot of that tedious work.
Definitely. Speeding up malware analysis hugely.
And deployment. How does this actually get used?
The idea is to integrate these models right into tools like IDEA Pro, maybe offer them as cloud services, upload binary, get an analysis back. The big challenge, though, as the source notes, is generalization. Getting models to work reliably across different platforms, compilers, optimization levels, that's still tricky. And right now, it's mostly focused on the code structure, less on data structures or memory layout.
Got it. Okay, so that's code analysis. What about threats we face daily, like dodgy Android apps? AI is working there too, right? Detecting malware.
Oh, absolutely. We've all worried about malicious apps. The source gives this great example of sophisticated Android ransomware. It misuses permissions, like System Alert Window, to draw over other apps. It even overrides user prompts to keep showing ransom notes. Nasty stuff. Machine learning helps app stores catch these before they get to your phone.
But this isn't the same deep learning approach we just discussed, is it? Uses a different pipeline.
Correct. This one uses dynamic analysis, basically running the app in a safe sandbox to see what it does. It extracts metadata permissions requested, APIs called, intents used, and feature engineering is key here. Out of like 50,000 Android APIs, they found they could get high accuracy focusing on just a small, critical subset. Around 426 key APIs linked to malware behavior.
Wow, only 426. That really narrows it down.
Exactly. It makes the analysis faster and more effective. They even added other features like requested permissions, which boosted precision and recall significantly. We're talking high 90s.
So what ML algorithm actually does the classifying?
They use a random forest algorithm. It takes those API logs, turns them into these one-hot encoded feature vectors. Basically, a simple way to represent which key APIs the app used. And this model, deployed in the real world, like the Tencent app market, showed really impressive results month after month. Over 98% precision, over 96% recall, consistently. Plus, the system evolves. They periodically update that list of key APIs to adapt to new app trends and SDK changes.
Okay, moving from apps to something broader, detecting weird events in sequential data, like system logs. This feels like finding a needle in a haystack.
It really is. Like reading a detective story in log files. The source focuses on anomalies in HDFS logs, that's Hadoop file system, and also network flows, using real-world datasets.
And the AI for this, what model do they use?
The deep LSTM autoencoder. LSTM stands for long short-term memory. It's good at remembering patterns over time. But this isn't just about spotting one weird event. It reconstructs the logic inputs. Think of those as the AI's internal predictions for what should happen next. The real innovation mentioned is DABlog, which uses a bidirectional LSTM.
Bidirectional. So it looks forwards and backwards in the log sequence.
Exactly. You can see context in both directions. The source points out that single-direction models often miss structurally abnormal sequences because they lack that bidirectional view. DABlog treats sequences as whole units, checks causality both ways. That makes it much better at spotting subtle structural anomalies, not just isolated weird events. It achieved F1 scores up in the high 90s on some datasets.
So it gets to the bigger picture, the whole sequence is context.
Precisely. But, like any system, it has challenges. Handling completely unknown event types, things they never saw in training, can still cause false positives sometimes.
All right, let's pivot to network attacks, DNS cache poisoning. A classic, but AI is offering new defenses.
Yet, DNS cache poisoning is tricky. It fools DNS servers into sending users to malicious sites. And because the attack packets often look technically correct, following protocol rules, signature-based detection can miss them. What's really interesting here is the data. There wasn't a good public data set, so they generated both good and bad traffic using protocol fuzzing.
Right.
Basically, intentionally messing with the DNS protocol to create tons of diverse malicious examples, and they could auto-label it.
That's clever. Generate your own training data. And the processing sounds complex too.
It is quite intricate. They take raw network traffic, select just 32 specific bytes from each DNS packet, carefully excluding things that might give away malicious domains directly so the AI learns the attack pattern, not just bad names. Then they chop this data by session, use a sliding window to create fixed-length sequences, and finally convert the numbers into individual bits. This bit-level representation helps the AI see control flags and nuances. The result: data samples that look kind of image-like.
Image-like, okay, that points toward.
A convolutional neural network, a CNN. Perfect for this kind of spatial image-like data.
And the results were phenomenal accuracy, precision, detection rate, all incredibly high, like 0.99 something. And for deployment, they used post-training quantization, which is a fancy way of saying they shrunk the model size dramatically from 452 kbd down to 41 kb with almost no hit to accuracy. Makes it super efficient for real-time network protection.
Amazing. Okay. Beyond specific attacks, AI is also used more broadly for malware detection and even clustering them into families, right?
Absolutely. Security teams face a deluge of new malware daily. The source talks about converting malware binaries into different formats for AI analysis.
Like those images you mentioned, a picture of the code.
Exactly that. Raw bytes become pixel values, 0 to 255, reshaped into a 2D image. Or they treat the binary as sequential data, just a stream of bytes, maybe broken into chunks. Or, and this is quite sophisticated, they extract control flow graphs, CFGs. It's like a flow chart of the program's execution paths. Nodes are code blocks, edges are the jumps between them.
And different AI models suit each format.
Yep. CNNs for the images, often using transfer learning from models like ResNet 50. Recurrent neural networks like LSTMs or GRUs for the sequential byte streams. And graph neural networks, GNNs, are specifically designed for those CFGs. The goal is always the same: teach the AI to spot similarities between different malware samples and tell them apart from legitimate software.
And that clustering part sounds vital for dealing with volume.
Totally crucial. Anti-malware vendors need efficient ways to group thousands of daily samples. After getting behavior profiles, watching what malware does using dynamic analysis and taint tracking, they use something called locality-sensitive hashing, or LSH. LSH is smart. It hashes similar malware profiles into the same buckets with high probability. It lets you quickly find similar malware families in huge data sets without comparing every single pair. Very scalable. Uses concepts like min-hash signatures and banding.
Okay, one last use case, and this one really blows my mind. Cross-version code similarity detection. Figuring out if two different-looking binaries came from the same original source code.
Yeah, that's a tough nut to crack. Huge implications for reverse engineering, finding reused vulnerable code, protecting intellectual property. Binaries can look vastly different just due to compiler choice or optimization flags. So the raw data here involves taking source code and deliberately compiling it many different ways to create pairs of binaries, some from the same source, some not.
And the AI learns to see past the surface differences, find that underlying source code fingerprint.
That's the goal exactly. Learn an embedding vector for each binary, a unique digital fingerprint. The trick is to make sure binaries from the same source end up with very similar vectors, while those from different sources are far apart in that vector space. A common approach is the Siamese network, two identical subnetworks sharing weights. They process pairs of binaries, similar to similar, and a contrastive loss function pushes similar pairs closer and dissimilar pairs further apart during training.
Clever. And how well does it work?
Pretty well. Models like IDIF, using sequence data and CNNs, show high recall for finding matching programs. Gemini, using graph data and GNNs, has great scores for matching individual functions. It's hard to compare directly, program versus function level, but both work. GNNs might need more domain knowledge, but are customizable. Sequence models are maybe easier to get started with. And active learning helps getting humans to label tricky examples really boosts performance.
Wow. Okay, so we've seen AI doing some seriously heavy lifting in cybersecurity, reverse engineering, malware detection, anomaly spotting, even code similarity. It's really becoming fundamental.
Mhm.
But that might leave you, our listener, thinking, okay, that's amazing, but how do I get involved? How do I learn this stuff? It can feel a bit daunting.
It definitely can. But that's where our other source, the Reddit discussion, comes in. It's packed with insights from people actively self-learning this. And the first, absolutely critical takeaway, echoed by so many experienced pros, is fundamentals are freaking important. Seriously, understanding why things work is way more valuable long-term than just knowing how to click buttons on a tool.
Okay, fundamentals first. Where does someone even start with those basics? What's the ground floor?
Networking. Over and over again, people stress this. Understand IP, TCP, UDP, ICMP, how apps talk across networks. That understanding opens up so much in security and just general IT fundamentals beyond that.
Are there specific certs or resources people recommend for building that foundation to make it a bit less abstract?
Yeah, definitely. CompTIA Network Plus and Security Plus come up a lot for baseline IT and security knowledge. Professor Messer's YouTube videos are a huge favorite, and they're free. Also, the ISC2 Certified in Cybersecurity is mentioned as a free starting point, which is great for accessibility.
Okay, foundation set. What about getting hands-on? Theory's one thing, doing is another.
This is where the self-learners really thrive, and the Reddit thread was full of ideas. Practical learning platforms. TryHackMe is super popular, especially for beginners, lots of free modules. Hack the Box is seen as a step up, more challenging. Then you've got Cyber Defenders, Blue Team Labs, Let's Defend, HackVisor, Attack IQ Academy, Cybery, Over-the-Wire CTFs. Loads of places to practice.
And building your own lab environment, a home lab, people really push for that, don't they?
Oh yeah, highly encouraged. And it doesn't have to break the bank. You can start cheap. pfSense, firewall free, open source, virtual machines, VirtualBox is free. Set up Kali Linux for offensive practice, Security Onion for defensive tools. For Windows stuff, look at trials from Microsoft Business Premium with Defender or the pay-as-you-go model for Microsoft Sentinel. Elastic Stack often has trials for log analysis. For Active Directory practice, there's something called GeoAd mentioned. And for web security, OWASP Juice Shop is fantastic. It's an intentionally vulnerable web app you can safely attack and learn from.
That's a ton of great practical stuff. What about learning by doing specific tasks, not just using platforms?
Great point. The advice there is super hands-on, like write your own vulnerable code. Simple SQL injection, cross-site scripting, whatever language you like. Then try to exploit it yourself. Then fix it. And crucially, document that whole process. Or, carefully, in an isolated VM, experiment. Disable a firewall. DMZ a server, see what happens. Cautiously, of course. Explore malware analysis. The source even mentions downloading ransomware again only in a secure, isolated VM and picking it apart with tools like Kedra. That's deep learning.
Okay, that's a lot of paths and tools. It's a broad field. How do you find your niche, your focus, especially as you move from beginner towards more advanced stuff?
Good question. A lot of advice boils down to figuring out what genuinely interests you. Are you drawn to offensive security? Red team stuff like pen testing, exploit dev, or maybe defensive security. Blue team, working in a SOC, incident response. There are also roles like security architect, IT auditor, GRC, threat intel, security software developer, even legal or training roles. A great tip was to watch security conference talks online, DEF CON, Black Hat, RSA, B-Sides videos on YouTube. See what topics grab you, what problems you find interesting.
And it's clear you can't just learn at once. Continuous learning is key.
Absolutely non-negotiable. This field changes constantly. Beyond formal training or labs, engage with the community. Discord channels, YouTube channels like the Cyber Mentor or Hackersploit, blogs like Hack Tricks. Listen to podcasts, Darknet Diaries, Security Weekly are mentioned, and networking with actual professionals at events. That's highlighted as one of the fastest ways to learn, just talking to people doing the job.
What about coding? We heard AI uses Python, involves complex models. The listener who sparked this mentioned C++ basics. How crucial is coding?
It's definitely an asset, though maybe not strictly essential for every single entry-level role. But it helps a lot. Python and Go get recommended often, especially for red team tasks where you might write custom tools. But even learning C++ teaches you so much about how computers actually work at a low level, memory management, pointers. That fundamental understanding is gold for finding security flaws. So yeah, coding is a big plus.
So wrapping this up, what's the big takeaway for you, our listener? We've seen how AI is fundamentally reshaping cybersecurity, automating analysis, predicting threats, finding subtle attacks. And we've also charted a course using advice from the community, making that journey from beginner to capable professional feel, hopefully, a bit more achievable.
Yeah, the main thing is there's no magic bullet, no shortcut to real understanding. It starts with that solid foundation networking, IT basics. Then it's about diving in, getting hands-on, build that home lab, break things safely, fix things, and always ask why. Why does this work? Why is this vulnerable? Engage with the community. That's the path.
Your journey isn't just about memorizing commands or tool names. It's about building that curiosity, that willingness to tinker and explore. What's the next surprising thing you'll uncover? What skill will you master? That's the exciting part of this landscape.
Keep exploring, keep asking questions, keep building. The resources, the tools, it's all out there. Time to dive in.